Imagine looking at a baby picture of the universe, not a fuzzy, low-resolution snapshot, but a sharp infrared image that lets you see structures only a few 100 million years after the Big Bang. That is what the James Webb Space Telescope is doing. Now imagine this. In those first cosmic baby photos, astronomers see objects that are too bright, too big, too early. They shine like tiny cosmic cities in a universe that should barely have had time to light a candle. And a group of theorists is saying something wild. Maybe these are not normal galaxies. Maybe they are not even normal stars. Maybe they are something more exotic. Giant, puffy, hydrogen and helium spheres, millions of times the mass of the sun. Powered not by nuclear fusion, but by dark matter, annihilation. They call them supermassive dark stars. If that idea is right, it would rewrite our story of how the first stars and the first black holes formed. If it is wrong, it still tells us something deep about how hard it is to make sense of the early universe. In this first part of a two-part Think Science special, we are going to walk through this dark star idea slowly. What are dark stars supposed to be? What exactly has JWST seen? Why do some astronomers think these observations line up with the theory? And why other researchers are still skeptical? Then, in part 2, we will look at what this would mean for dark matter, for the first black holes, and for our Big Bang timeline, if dark stars really existed. For now, let us start with the puzzle that JWST dropped in astronomers' laps. Pause it for a second and picture the universe about 300 to 500 million years after the Big Bang. The cosmos is still very young. Dark matter has already clumped into halos. Ordinary gas has started to fall into those halos. The first stars and galaxies are just beginning to switch on. In the standard picture, those first stars, called population to 3 stars, formed from almost pure hydrogen and helium. They are massive and bright, but they are still stars powered by fusion in their cores. They light up small, fragile galaxies. Those galaxies slowly merge and grow. It takes time to build big, bright systems. Then JWST comes online. Using its infrared eyes and the trick of gravitational lensing, it can see galaxies at redshifts 10, 12, 13, and beyond. That means we are seeing them just a few 100 million years after the Big Bang. Right away, something looks off. Some of these objects are too bright and too massive for their age, if they are normal galaxies made of normal stars. At least that is what our best computer simulations were saying before JWST flew. WST flew. Out of that confusion, one group of theorists saw an opportunity. Back in the late 2000s and early 2010s, Catherine Fries and collaborators developed a strange idea. What if the very first stars were not powered by fusion at all? What if they were powered by dark matter? This is where we need to talk about what dark matter is and how it can release energy. You have probably heard the line that dark matter makes up most of the matter in the universe. It does not emit light. It does not absorb light. We only know it is there because of its gravity. One leading idea is that dark matter is made of new kinds of particles that can annihilate when they collide. When that happens, they turn their mass into energy, mostly in the form of other particles and radiation. Normally, dark matter is spread out and cold. those particles almost never run into each other. But in the dense centers of early dark matter, halos, the density can be higher. If gas is collapsing into the same region, something interesting can happen. The dark matter particles can get trapped in the deep gravitational well created by that collapsing gas. Their density in the core goes up. The rate of annihilation goes up. Suddenly you have a tiny region in space where dark matter is quietly dumping energy into the gas cloud from the inside. Fraser and colleagues asked a simple question. What if that dark matter heating is strong enough to stop the gas from collapsing into a tiny, hot fusion core? What if instead it puffs the gas up into a large, cool, but incredibly bright object? That is the birth of a dark star. Despite the name, a dark star would not be dark. It would actually be extremely bright. It is called dark because its power source is dark matter, not fusion. These early dark stars start small, but the dark matter heating keeps the gas extended and relatively cool compared to a normal protostar. That extended structure can keep sucking in more gas from its surroundings. In the models, dark stars can grow huge. Tens of thousands, hundreds of thousands, even up to 1 million solar masses. Their luminosities can go up to 1 billion times the sun or more. They are like cosmic lanterns powered by invisible fuel. They are also predicted to live much longer than a normal massive star. As long as dark matter continues to annihilate in the core, the star can stay puffed up and shining. When that power runs out, the star can finally collapse, very likely forming a massive black hole seed. For a long time, this stayed in the realm of theory, something that might exist, but with no obvious way to detect it. Then, JWST arrived, and astronomers started seeing very bright, very distant objects with surprisingly small sizes on the sky, and surprisingly intense spectra. In 2023, a team led by Cosmin Illy and Catherine Fries looked at some of the most distant sources in one of JWST's deep fields. In particular, they studied 3 objects with names like JADES G130 and JADES GS110. These objects sit at redshifts between about 11 and 14. So again, we are looking back to when the universe was only a few 100 million years old. Those objects were galaxies made out of fusion-powered stars. They would have to be incredibly compact and incredibly efficient at turning gas into stars. More so than most models expect that early. The team asked, could these be single supermassive dark stars instead of entire galaxies? They took their dark star models, including how these objects would emit light at different wavelengths, and compared them to the JWST photometric data. At the level of broadband colors, they found that supermassive dark stars with masses around 1 million suns could match the observed brightness and spectra. That was the first claim that JWST might have already seen candidates for dark stars. At that point, critics could rightly say, photometry alone is not enough. Lots of different objects can have similar broad colors. You need spectra. Fast forward to 2025, and the field gets another jolt. JWST's NIRSpec instrument, which can take detailed spectra of very faint objects, has now collected spectra for several ultra-distant sources, including some of those original candidates and some new ones. In a new paper accepted in 2025, Illy, Fries, and collaborators looked at the spectra of 4 of the most distant known objects. They found that all 4 are consistent with dark star models, and one object in particular shows something extra. A clear absorption feature at a wavelength around 1640 angstroms in the rest frame, but that feature corresponds to singly ionized helium. In their models, that helium signature is expected to be a sort of calling card for a dark star atmosphere at the right temperature. In other words, not only are these objects bright enough and compact enough to be dark stars, one of them also has a spectral fingerprint that the models predicted dark stars should have. At the same time, a press release from Colgate University and other outlets describe this as possibly the best evidence yet for supermassive dark stars powered by dark matter annihilation. So is that it? Case closed. Dark stars are real, but not quite. Other astronomers point out that these objects might still be explained as very compact, star-forming galaxies, or as systems built around rapidly growing black holes. There is a whole zoo of ideas for unusual objects in the early universe. You might have heard about black hole stars or quasi-stars. In those models, you also have a huge gas envelope with an energy source in the center. But in that case, it is an accreting black hole rather than dark matter. In some scenarios, the earliest black holes could grow inside such envelopes and look, from far away, like single extremely bright objects. On top of that, extracting clean spectra at these redshifts is hard. You are working near the edge of what JWST can do. You have to subtract background, account for lensing, and work with very faint signals. So when one team says a helium feature at 1640 angstroms is a smoking gun for dark stars, others want to see independent analysis and more data before they accept that label. Even the dark star team is cautious in their formal papers. They talk about candidates, not confirmed detections. But the big point is this. Before JWST, dark stars were a neat but very speculative idea. Now we have actual objects on the sky whose properties are at least consistent with the dark star hypothesis. And this connects to another major mystery that JWST has highlighted. The universe seems to have supermassive black holes very early. We are talking about black holes, millions or billions of times the mass of the sun already in place less than 1 billion years after the Big Bang. Growing something that big so fast with normal stars and normal gas accretion is tough. Dark stars offer a possible shortcut. If you can build 1 million solar mass dark star in a dark matter halo, and then collapse it, you suddenly have a very heavy black hole seed. From there, it is much easier to grow into the monsters we see at the centers of early quasars. So the dark star story is not just about exotic stars. It is tied to the question of where the first giant black holes came from. In this first part, we have set the stage. JWST is seeing objects that are too bright and too big too early. Terry says the first luminous bodies might have been powered by dark matter rather than fusion. A series of papers has argued that specific JWST objects can be matched by supermassive dark star models. And new spectra have added a possible helium signature that lines up with that picture. At the same time, the community is divided. Are these dark stars, weird galaxies, black hole stars, or something else? What is clear is that the early universe is more complicated than our simple textbook story. In part 2, we are going to push deeper into the implications. How exactly does dark matter annihilation power these stars? How do you build one from a collapsing halo? What would it mean for dark matter? Physics, if dark stars are real? And how will future JWST observations, and maybe future telescopes, confirm or kill this idea. We will also look at some of the strongest counter-arguments. Why some researchers think dark stars are unlikely, and what alternative stories they prefer for these ultra-bright early objects. For now, I will leave you with a question. If the first lights in the universe were not fusion-powered suns, but dark matter-powered giants, does that make the universe feel stranger to you, or more unified? Because in that picture, the same invisible stuff that shapes galaxies by gravity also literally lights up the first stars. Let me know what you think, and stay tuned for part 2, where we follow these possible dark stars all the way to the birth of the first supermassive black holes. In part 1, we left the story at a crossroads. JWST had shown us objects that look too bright and too big too early, and the dark star idea stepped forward as one possible explanation. Now it's time to push deeper. In this second part, we are going to ask 3 big questions. First, how exactly does dark matter annihilation keep a dark star alive? Second, what would it mean for the first black holes and the history of the early universe if dark stars are real? Third, what observations in the next few years will confirm or kill this idea? And along the way, we will compare dark stars to their rivals, black hole stars, compact baby galaxies, compact baby galaxies, and other exotic objects that JWST may be seeing at the cosmic dawn. Let us start in the core of a dark matter halo. Picture a dark matter halo a few 100 million years after the Big Bang. It is made mostly of dark matter, but it also contains a smaller amount of normal gas, hydrogen and helium, with almost no heavier elements. As time passes, that gas begins to cool and fall toward the center. Gravity pulls it in. It loses energy, collapses, and starts to build a dense core. When the gas collapses, the dark matter cannot just sit there. Its distribution changes too. It gets pulled into a steeper, denser cusp by the gravity of the gas. Now you have 2 components in the same small region. A dense clump of hydrogen and helium gas, and a steep spike of dark matter particles moving through that gas. If dark matter consists of particles that can annihilate when they meet, something important happens. The annihilation rate goes like the density squared. You increase the density, and the energy output climbs very fast. Those annihilations release energy, not in the form of light beamed straight at us, but in the form of particles and radiation that get absorbed by the surrounding gas. That energy heats the gas from the inside. At first, the collapsing cloud does what any protostar would do. It tries to shrink. Gravity squeezes it. The center heats up, but as the dark matter density rises, the annihilation heating becomes strong enough to fight back. Instead of collapsing all the way to a tiny scorching fusion core, the gas gets held up. It puffs out into a large, bloated object, cooler at the surface than a typical massive star, but with a huge radius and a huge total luminosity. That is the basic engine of a dark star. The star is made almost entirely of hydrogen and helium. Inside, gravity is trying to squeeze. Dark matter annihilation is providing a gentle but persistent heat source. Hydrostatic balance is reached at a much larger radius than normal. While this is happening, the star is not just sitting there. It is still accreting gas from the halo, because it is cool at the surface compared to a normal massive star. It does not blast its surroundings with as much ionizing radiation early on. That means it does not blow away its own fuel as aggressively. In the simulations, that combination is powerful. The star stays puffed up. It stays relatively cool at the surface. It keeps swallowing gas for a long time. Over time, a dark star can grow from a few tens of solar masses to thousands, then to hundreds of thousands, and in some models up to around 1,000,000 times the mass of the Sun. At that size, it is not a star in the everyday sense anymore. It is a supermassive object with the density structure of a star and the brightness of a small galaxy. On the outside, to a telescope like JWST, it looks like a very compact, extremely luminous source. On the inside, the power source is still dark matter, annihilation, in the central regions. Eventually, the dark matter fuel runs low. The annihilation rate falls. The heating cannot keep up with gravity. The star can no longer stay bloated and stable. At that point, models predict a catastrophic collapse. Because the star is so massive, it does not gently shed its outer layers like a normal star. Instead, it can collapse almost directly into a massive black hole, potentially with a mass of 100,000 suns or more. That is where dark stars connect directly to one of the biggest puzzles in modern cosmology. How did the universe build supermassive black holes so fast? JWST and other telescopes have now found black holes tens of millions of times the mass of the Sun, less than 1 billion years after the Big Bang. Growing those from ordinary stellar mass black holes, just a few tens of solar masses, is very hard on the available timeline. You either need black holes that eat at nearly the maximum possible rate for hundreds of millions of years, or you need to start with much heavier seeds. Supermassive dark stars offer those heavier seeds. If each dark star collapse leaves behind a black hole of, say, 100,000 solar masses, then you have given the universe a head start. From there, normal gas accretion and mergers can much more easily build the monsters that power the earliest quasars and the mysterious little red dots that JWST is seeing. As if dark stars exist, they are not just a curiosity. They would be a missing chapter in the story of how black holes, galaxies, and large-scale structure evolve. Now, what does this idea say about dark matter itself? For a dark star to work, dark matter has to do two key things. It has to annihilate when particles meet. And it has to annihilate strongly enough at the densities in early halos to provide meaningful heating. This lines up naturally with one of the classic dark matter candidates: weakly interacting massive particles, or WIMPs. In many WIMP models, the annihilation cross-section and particle mass are such that, in dense regions, annihilation can produce a steady trickle of energy, not enough to blow everything apart, but enough to act as a gentle internal furnace. If JWST really is seeing dark stars, that would be indirect evidence in favor of an annihilating dark matter particle. It would not tell you the exact mass or interaction strength by itself, but it would tell you that dark matter is not perfectly inert. On the flip side, if future observations rule out dark stars, that removes one piece of circumstantial support for those WIMP-like models. This is why theorists are excited. We are not just talking about a weird type of star. We are talking about a new way to probe dark matter physics using the first luminous objects in the universe. So how do we actually tell if any of these candidates are dark stars and not something else? Astronomers are focusing on three main kinds of evidence. First, the overall brightness and size. The detailed spectrum, especially near certain key wavelengths. Third, the environment around the object. We talked in part 1 about size and brightness. Supermassive dark stars are expected to be incredibly luminous, but quite compact. They sit alone, like single brilliant points of light, rather than like extended galaxies. Spectra are the next big test. When you pass the light through a spectrograph, you spread it into a rainbow and look for specific features. Absorption lines, where particular elements in the atmosphere soak up certain colors. Emission lines from hot gas around the object. In the latest work, the Dark Star team has focused on 4 ultra-distant objects with JWST spectra. One of them, JWST 14.0, shows a feature at about 1640 angstrom in the rest frame. That feature lines up with singly ionized helium. In their models, a helium line at that wavelength is expected as a kind of signature of a dark star atmosphere in the right temperature range. That is the so-called smoking gun that triggered all the headlines about dark stars in late 2025. But things got complicated fast. Another facility, the ALMA Observatory in Chile, picked up what looks like an oxygen emission line from the same object. And oxygen usually means at least some prior generation of fusion has already happened somewhere nearby. If both the helium absorption and the oxygen emission are real and robust, then JWST 14.0 might not be a single isolated dark star. It could be a dark star embedded inside a more complex metal-enriched environment. Or it might not be a dark star at all, but some mix of star formation and black hole activity. Either way, the message is clear. These candidates are living in messy, real astrophysical settings. Not in the idealized isolation of a computer model. That is why independent teams are now reionizing the same spectra, checking the line, identifications, testing whether simpler models using ordinary stars and gas can fit the data just as well. And while that battle is going on, another rival idea has stepped into the ring. The black hole star. In that model, you again have a huge gas envelope. But instead of dark matter annihilation in the core, you have a rapidly feeding black hole. Gas falls toward the black hole, heats up, and pours out radiation that puffs up the envelope and makes the whole system shine. From far away, both a black hole star and a dark star can look like a single extremely bright compact object. Distinguishing between them requires careful work on the spectrum, the variability, and the long-term evolution. Normal compact baby galaxies are still in the running too. JWST has already shown us that some early galaxies are more efficient at forming stars than we expected. Some researchers argue that, with updated simulations and slightly more extreme assumptions, we might not need exotic objects at all to explain many of the bright sources. So what will actually break the tie? First, more spectra at higher signal-to-noise. JWST is still collecting data. For some of these candidates, we only have a few hours of exposure. More time on target will sharpen the lines, reduce the noise, and let astronomers test whether features like the helium 1640 line and the oxygen line really hold up. Second, better modeling of all the options. Teams are building libraries of predicted spectra for dark stars, black hole stars, and compact galaxies under a wide range of conditions. Those libraries can be fed into automated fitting codes that try to match the observations without human bias. Third, statistics. Right now, we are arguing about a handful of objects. In the next few years, JWST will find many more ultra-distant sources. If dark stars are real and common, their fingerprints should show up repeatedly. If they are rare or do not exist, the population will lean toward more conventional explanations. Future telescopes. The Nancy Grace Roman Space Telescope will survey huge areas of sky in the infrared, catching many more bright, early sources. Giant ground-based telescopes with 30-meter mirrors will be able to take sharper spectra, potentially detecting finer details in the atmospheres of these objects. On the theory side, there is also work to test the internal consistency of the dark star picture. If dark stars are common, they should affect other aspects of early cosmic history. They would contribute to the reionization of the universe in a particular way. They would leave imprints on the pattern of early galaxies. They would change the predicted distribution of black hole masses at later times. So theorists are checking whether you can have enough dark stars to solve the black hole problem without overdoing their impact on other observables. It is a delicate balancing act. Right now, the state of play looks like this. The dark star team has a coherent model with clear predictions. They have identified several JWST objects whose brightness and spectra are at least consistent with that model. Other researchers are intrigued but unconvinced. They point to alternative explanations based on more conservative physics. They highlight the ambiguities in the current data and the tension introduced by features like the oxygen line. Everyone agrees on one thing. The universe at cosmic dawn is more surprising than we thought. Whether these little red dots and bright specks turn out to be dark stars, black hole stars, extreme galaxies, or some mixture of all three, they are forcing us to rewrite our mental picture of the first billion years. So where does that leave us? If dark stars are real, then the first lights in the universe were powered by the destruction of dark matter particles. They would be a direct link between the invisible cosmic scaffolding and the visible beacons that lit up the early sky. They would help explain why giant black holes appear so quickly in the JWST data. They would give us a new way to probe the nature of dark matter. And they would add an entirely new chapter to the life stories of stars. If they turn out not to exist, that is still a powerful result. It would tell us that dark matter is more inert than the dark star models require. It would push us back toward explanations based on gas physics, black hole growth, and galaxy formation alone. And it would still leave JWST with the job of explaining the weird brightness of some of these early sources. Either way, the next few years of JWST observations are going to make or break some bold ideas. So the next time you see a JWST deep field photo with tiny red specks scattered across the darkness, try this. Pick one of those dots in your mind. Imagine it is a single bloated star, 1,000,000 times the mass of the sun. Imagine its core filled with dark matter, particles annihilating quietly, holding the whole structure up. Imagine that. When it finally dies, it collapses into a massive black hole that will still be there billions of years later. Then zoom back out. Because somewhere in that same image, another dot might instead be a black hole star, or an ultra-compact baby galaxy. Right now, we do not know which story is right, but we do know this. For the first time, a telescope is powerful enough to turn these speculative ideas into testable science. And that is maybe the most exciting part. The universe is not just giving us pretty pictures. It is forcing us to decide whether the first stars were born from ordinary fire or from the darkness itself. I will leave you with a question. If you had to place a bet today, would you bet that JWST has already seen a dark star? Or do you think the answer will end up being something less exotic, but no less interesting? Let me know what you think. And as always, stay curious.